Hello students, welcome back to the classroom point. In our today's class, we are going to discuss the valence shell electron pair repulsion theory. So in this theory, we will discuss the shape of the molecules and how the shape of molecules are generated using the electronic interactions among the valence shell electron pairs. So the main basis for this theory is the electronic interactions among the valence shell electron pairs. So basically, Lewis dot structures or Lewis theory was unable to explain the covalent bond molecules shapes. So that was rectified in the valence shell electron pair repulsion theory. So let us see the main points and the structure of the few molecules of the valence shell electron pair repulsion. So let's begin the class now. So the theory is valence shell electron pair repulsion theory. If you take the first letter of every word, we can get its abbreviation, which is known as the VSEPR theory also. So according to this theory, the repulsions among, you can see here, the repulsions among the electron pairs present in the valence shell of the central atom will decide the shape of the molecule. So that here we can say that basically this theory will explain the shape of the covalent molecules. And the shape of the covalent molecules depends upon the electron pair repulsions of valence shell of central atom. So these electronic repulsions in the valence shell of the central atom will decide the shape of the covalent molecules. Then the shape of the molecule depends upon the number of electron pairs. That means number of valence shell electron pairs. So let us see how many type of the electron pairs are present in the valence shell of a central atom. Usually a central atom may have either one type or both the type depending on the type of the molecule. So if the central atom, there are a chance to get either one type or two type, but let us discuss the both of the types. It may have the lone pair of electrons in its valence shell as well as the bond pair of electrons. This lone pair of electrons are concentrated towards only one nucleus. Let us take an example here. If you take the atom A, in that lone pair of electrons if present, the lone pair looks like this. So these both of the electron pairs which are not participating in the bond formation, they are attracted to only one nucleus. That's why only one side particular attraction is there, other side attractions are absent. Hence they occupy the larger volume. So that we can say that lone pair occupy the larger volume. And when they occupy the larger volume, obviously they cause the more repulsion. When it comes to the bond pair electrons, these bond pair of electrons are nothing but the shared electron pairs, because these are the electron pairs shared between the both of the bonded atoms. If you take an example here, AB molecule, so there is a bond, imagine, between the both of these AB atoms. Now this electron pair is concentrated or attracted to the both of the bonded atoms nucleus. So that is the reason why both sides it is stretched somewhat so that its volume gradually decreases. So here we can write down that bonded electron pair occupy less volume. When they occupy less volume, obviously they cause the less repulsion. So here bonded electron pairs causes the less repulsion. So now if a particular central atom is having both lone pair of electrons as well as the bond pair of electrons. Then repulsions comparison we can estimate in such a way that since lone pair causes more repulsion, so the repulsions between the both lone pair of electrons are greater than the lone pair bond pair repulsions, which are greater than the bond pair repulsions. Then everything is okay here, even though the repulsions are deciding the shape of the molecule and the number of electron pairs are deciding the shape of the molecule. Then the arrangement of this number of electron pairs around the central atom always arranged to minimize the repulsions. That means whatever the electron pairs are present around the central atom, these electron pairs arrange around the central atom in the space in such a way that to minimize the repulsion. So lesser the number of repulsions, more will be the stability to the molecule. Hence that arrangement gives the shape to the covalent molecules. Now let us see few examples how these number of lone pair of electrons are arranged in the different molecules. Shape of the molecules. This is also known as the geometry of the molecules. So the molecules can be taken in two ways. Molecules without lone pair of electrons, without lone pair of electrons on central atom, so this type of molecules are known as the symmetrical shape molecules. Symmetrical shape molecules in the sense if all the atoms present around the molecule are same type, then it is called as symmetrical shape molecules, or we can call this one as a regular shape molecules. The second category is with lone pair of electrons. With lone pair of electrons on central atom. So whenever lone pair of electrons are present on the central atom, they causes the repulsion so that they push the bonds go away from them. That's why the shape of the molecule completely changes. So such type of the shapes are called as either unsymmetrical or distorted shapes. So here we can consider this one as the unsymmetrical or distorted shape molecules. Now let us combine both of these to understand the valence shell electron pair repulsions in a good way. So let us take an example. So first category is molecules with two lone pair of electrons. That means total electron pairs. Electron pairs in this category is only 2. So here I am taking this some notations. Here in all these cases remember that A means central atom, B meaning is bond pairs, E meaning is lone pairs. So in this particular case, total number of electron pairs around the central atom is equals to only 2. So let us take in that both bond pairs are 2 and lone pairs are 0. Means imagine there is no lone pair, only bond pairs are there. Then these two bond pairs arrange around the central atom only to minimize the repulsions so that they arrange opposite to each other. Both of these bonds arrange opposite to each other. So this looks like a linear shape. So that shape of the molecule is linear and the angle between both of these bonds is 180 degrees. So let us take few examples for this. Here you can take the BeCl2 molecule, HgCl2 molecule have the linear shape and bond pair of electrons are 2. Second category is total electron pairs. Total electron pairs are 3. And before that, let us imagine what if one bond pair, one lone pair is there. In such cases, we cannot decide the shape of the molecule because only one side is there. Bond angle does not exist. That can be considered as the linear molecule only. So now, when it comes to the electron pairs are totally 3. In that, bond pairs are 3, lone pairs are 0 in this category. So that the central atom, around the central atom, the bond pairs try to arrange in this manner so that here bond, here one bond and here another bond. So the bond angle among these any two bonds is 120 degrees. Here 120, here also 120, here also 120, totally 360 degrees. This is called the trigonal planar shape. Trigonal planar in the sense, in this plane, all the atoms are present in the same plane. For example, A is here, 1B is here, 1B is here, 1B is here. So that they are arranged like this. So the all are in the same plane, having the bond angle 120 degrees. And here 1, 2, 3, 4. That means these 3 atoms and this atom, all the 4 atoms are in the same plane. Hence it is called the planar shape. But 3 corners are there. Hence it is called the trigons. So trigonal planar. Example is BeCl3 molecule. In this category, let us see the one more option. What if 2 bond pairs are there? Bond pairs are 2. And lone pair is 1 is present. So when 2 bond pairs are there, obviously they occupy these places. If one lone pair is there, it has to occupy one of these places. Among all these, one of the places has to be occupied by the one lone pair of electrons. So that the shape, here bond pair, here bond pair, here lone pair of electrons are present. That is what E. Now, in this case, only bonds are there. Bond pair repel each other so that to minimize the repulsions, they are arranging in this manner. But in this molecule, lone pairs occupy the larger volume than the bond pairs. So, when lone pairs occupying the larger volume, they causes the larger repulsions between the lone pair, bond pair repulsions. That's why these bonds are pushed to come closer to each other. Hence, this bond angle is less than the bond angle present in this molecule. So this shape is called as the angular shape, or it is also known as the bent shape or reversed V shape. Example, SO2 molecule and O3 molecule. These lone pairs are pushing these bonds closer to each other. Depending on the size of this atom, this bond angle will come. Now, if you see here, if the size of this central atom is larger, then the bonds can arrange away from each other so that angle increases. If the size of the atom is smaller, then both of the bonds has to come closer. Why? Because this smaller size cannot accommodate these two bonds away from each other, so that the lone pair, bond pair repulsions are more if the A atom, that means central atom, is smaller in size. That means if you take the SO2 and O3, the bond angle in O3 is less than the SO2. Third category, total number of electron pairs. If 4 are present, Then imagine condition 1. All those are bond pairs and lone pairs are 0. Then the arrangement of the atoms around that particular central atom is in this manner. So this shape is called as tetrahedral. So tetrahedral in the sense it is having the 4 faces. The bond angle here is 109.5 degrees. Example, we can take the CH4 molecule, NH4 plus ion, etc. Second category in that, if bond pairs are 3 and lone pair is 1, that means out of these 4 positions, one of the position has to be occupied by the lone pair of electrons, rest of the 3 positions to be occupied by the bond pairs. So example, let us take the A atom. This place is occupied by the lone pair of electrons. Imagine the remaining 3 places to be occupied by the bond pair of electrons. Now in this case, we can observe that lone pair, bond pair repulsions can present, at the same time bond pair repulsions also present. So this lone pair will push these bonds come closer to down or each other. As a result, the bond angle in this case is less than the bond angle in this case. So this molecule is not having any type of the lone pair of electrons. That's why these shapes are called the regular shapes. And this is having the lone pair of electrons, so that because of the presence of lone pair of electron, the shape of the molecule is somewhat disturbed. That's why this shape is called the distorted shapes. So this distorted shape, which looks similar to the tetrahedral, is known as the pyramidal. Example, ammonia, in which bond angle is 107 degrees. Now, out of these 4 electron pairs, now let us imagine 2 bond pairs are present and 2 lone pairs are present. Then again, out of these 4 places, 2 must be occupied by the lone pair, remaining 2 has to be occupied by the bond pair of electrons. Now see this one, here 1 lone pair of electron is present, here 1 lone pair of electron is present, here 1 bond pair, here 1 bond pair is present. So when you compare these molecules, here lone pair repulsions, lone pair repulsions, bond pair repulsions, all the 3 type of electronic repulsions are present. In this case, only lone pair bond pair repulsions are present. Lone pair repulsions are absent. Here only bond pair repulsions, no lone pair repulsions are present. So here, since lone pair repulsions are greater than the lone pair bond pair, so these both lone pair of electrons causes the bond angle to decrease. Why? Because they push this till these bonds come closer to each other. That's why bond angle decrease here. This shape is called as, it looks like V shape or angular shape. Example, H2O molecule, in which the bond angle is 104.5 degrees. So if you observe one thing very clearly, from here to here, in here to here, even though they are having the same number of electronic pairs, electron pairs category is only 4. Here 4 electron pairs, here also 4 electron pairs, here also 4 electron pairs. But here all electron pairs are bond pairs. Here 1 is lone pair, remaining 3 are bond pairs. Here equal number of bond pairs and lone pairs are present. Now, when the number of lone pair of electrons increases, the repulsions between the electron pairs also gradually increase. That's why their shape changes and bond angles gradually decrease. So it is very clear that molecules having the same number of electron pairs, valence electron pairs, when the number of lone pair of electrons increase, gradually the bond angle decreases. Now let us see another category. Electron pairs. Imagine 5 electron pairs are there. In these 5 electron pairs, all are bond pairs and lone pairs are 0. Then we get the molecule like this. Five bond pairs are present. So in these 5 bond pairs, these are the bonds, trigonal planar shape, and these are the 2 pyramids. So this is called the trigonal bipyramidal shape. In these bonds which are on the plane, this bond, this AP, this AB, this AB, these 3 bonds are present on the same plane. That's why these bonds are known as the equatorial bonds. So E stands for the equatorial. And these 2 bonds are perpendicular to this plane. Exactly. These are known as the axial bonds. So this type of the molecules, trigonal bipyramidal shape, are having the 2 type of the bonds. They are equatorial bonds as well as the axial bonds. This equatorial bond angle is 120 degrees, whereas axial bond angle with the equatorial plane is 90 degrees, and axial bond angle is 180 degrees. So here 3 type of the bond angles are present: 120 degrees, 90 degrees and 180 degrees. Now let us take an example of this molecule. The molecule is PCl5. We need to discuss more about this particular PCl5 molecule as well as this particular bond. So I'll take an example of the PCl5. In PCl5, as we call, these are all equatorial bonds. These are the axial bonds. Axial bonds are making 90 degrees angle with the equatorial bonds. That means this axial bond gets repulsion from this bond, this bond, this bond with 90 degrees. Similarly, this one also gets the repulsion from all these 3 bonds because it is also having the 90 degrees. Since these 2 bonds are facing the more repulsions from both of these 3 bond pair of electrons, they go little bit away from the central atom. As a result, this bond P chlorine, this P chlorine, in this case AB and AB, that means axial bond lengths increase because the repulsion causes these bonds to go away from each other. That's why bond length, if you take that, axial bonds are greater than the equatorial bonds. And equatorial bond lengths are less. Why? Because they get repulsion only from this bond and this bond, not from the other one. So the number of repulsions caused for this equatorial bonds are very less. And one more, this equatorial bond angle is 120 degrees. That means these bonds are arranged, these atoms are arranged on the equatorial plane very much away from each other. So that is the reason why they feel less amount of the repulsion. But whatever the atoms are present in the axial plane, they get the more repulsion. That's why their bond length gradually increases. Now, whenever the PCl5 molecule participate in the chemical reactions, first these 2 chlorines will participate in the chemical reactions. The reason is these bond lengths are more, so longer bond lengths. That's why bond enthalpy is less. So we need the less amount of energy to break both of these bonds. Hence, these chlorine atoms participate in the chemical reactions first. And what happens if another molecule is taken? Imagine if PCl2 F3 is taken. If different atoms are present In such cases, always larger atoms occupy the equatorial places, smaller atoms occupy the axial places. Because in axial places, bond angle is less, they get more repulsion. So the smaller atoms, if they are placed in these places, they minimize the repulsions. But if you place the larger atoms in axial places and smaller atoms in the equatorial places, larger atom gets the more repulsions which destabilize the molecule. So now let us see the example. Between chlorine and fluorine, chlorine is the larger atom, so that chlorine atoms occupy the equatorial places, remaining 3 places to be occupied by the fluorine atoms. Now, if we take another example of that, PCl3F2, if this molecule is taken, then the shape could be looks like this: phosphorus, chlorines, 3 chlorines occupy the equatorial places and 2 fluorines occupy the axial places to minimize the repulsions and to give the stability to the molecule. Now in this case, all the bonds are opposite to each other. Here dipole moment equals to 0. Here dipole moment not equals to 0, because these 2 bonds can be cancelled, because the moment coming from these 2 chlorines cannot be cancelled by the third phosphorus fluorine bond. So in this way, if all 5 bond electron pairs are present and 0 electron pairs are there, then the shape of the molecule looks like this in the category of the electron pairs of 5. Now let us introduce the lone pair of electrons here. Second category, 4 bond pairs and introduce 1 lone pair. In such cases, imagine lone pairs occupy always equatorial places to minimize the repulsions because angle is more. Bonds always occupy the axial places and rest of the equatorial places. So in this case, we can consider the shape of the molecule looks like this. Lone pairs occupy the equatorial places, remaining 4 places occupied by the bond pair of electrons. So this type of the shape is called the seesaw shape or folded square, or we can call this one as a distorted trigonal bipyramid. Example for this is SF4 molecule. Third category in this is bond pair of electrons are 3, lone pair of electrons are 2. Then obviously lone pairs occupy the equatorial places, so that the molecule looks like this. Now this is called, if you turn the molecule like this, it looks like a T shape. Example, ClF3 molecule. Now if you observe all these cases, whenever we are deciding the shape or whenever we are naming the shape of the molecule, we are not considering the position of the lone pair of electrons, we are considering only bond pair of electrons. Otherwise, all these molecules to be called as the same trigonal bipyramidal shape. But this is called the trigonal bipyramidal shape because 5 bonds are present. In this case, only 4 bonds are present. That's why it is named with a different name, that is seesaw structure. Here only 3 bond pair of electrons are there. That's why ignoring the position of the lone pair of electrons, we are giving name to this molecule as T-shaped molecule. So let us see the other category. Total number of electron pairs, 6 are present. So in this first category, all are bond pair of electrons, and 0 lone pair of electrons are present, then the shape of the molecule so A and all the 6 places to be occupied by the bond pairs. This is known as the octahedral shape, and all bonds are, this is, if you take x-axis, y-axis, this is z-axis. That means the bond angles between any two bonds is 90 degrees, side by side bonds. So that here opposite bonds bond angle is 180 degrees. Here also 180 degrees. Here also 180 degrees. But nearest bond angle is 90 degrees. So here this is 90 degrees. This is 90 degrees. This one also 90 degrees. Any two nearest bond angle is 90 degrees. But opposite bond angle is 180 degrees. This one also opposite bond angle is 180 degrees. So the question is, how many 90 degrees bond angles are present? You can see that this particular pyramid will get the bond angle from 9 degrees from this bond, this bond, this bond and this bond. That means this bond is getting the 4 from the plane, and similarly this bond also will get the 90 degrees bond angles from the bottom side. So 4 plus 4, 8, and these bonds also will get the 90 degrees bond angle with respect to bonds of the same plane. That's why there are 12 90 degrees bond angles are present. And how many 180 degrees bond angles are present? Opposite bonds are having the 180 degrees. That's why here 3 180 degrees bond angles are present. Example for this molecule is SF6 molecule. Now in this only, let us introduce one more category. That is, bond pairs are 5, but electron pair is 1. So out of these 6 places, one of the places to be occupied by the electron pair, that means lone pair of electron. So remaining places to be occupied by the bond pair of electrons. Imagine the molecule looks like this. Lone pair of electrons and down bond pair of electrons. So this is actually octahedral, means 2 pyramids are there, above the plane and below the plane. Here only one pyramid is there. That's why it is called the square pyramid. Example, BrF5 molecule. Dear students, I hope you understand this class of valence shell electron pair repulsion theory, which decides the shape of the molecule, and final end is, you should remember one point, that any molecules, any two molecules having same number of bond pairs and lone pairs, that molecule will have the same shape. Example, and if you take here is H3O plus, which is having the 3 bond pairs and 1 lone pair. Similarly, NH3 is also having the 3 bond pairs and 1 lone pair. So total number of electron pairs in this case is 4, here also 4. So whenever number of electron pairs around the central atom is the same, at the same time having the same number of bond pairs and lone pair of electrons, then their shape also to be same. So this is today's class, and we shall meet in the next class. Thank you one and all.